Hello to everyone. My name is Maria Markovska. I'm a teaching assistant at the Faculty of Electrical Engineering and Information Technologies from Skopje, Macedonia. The title of the video material that I'm going to present is LabVIEW-based application for automatic detection and classification of power quality disturbances. Here, I want to accentuate that this video material is part from the project titled as Innovative Teaching Approaches in Development of Software-Designed Instrumentation and its Application in Real-Time Systems. This project is supported by the Erasmus Plus program, the key action 203, titled as Strategic Partnership for Higher Education. Now we can start with the presentation. Here is the outline of the presentation. Firstly, I will give some introduction about power quality and about the developed application. I will present the main stages in the developed application. I will talk about the feature extraction method that is used, the discrete wavelet transform used as a signal processing tool, the wavelet-based features, and the implementation of the feature extraction method in MATLAB. I will talk about the classification method that is used, the random forest algorithm, its implementation in MATLAB, and I will present some experimental results that are important for the accuracy of the classifier that is implemented in the developed application. After that, I will demonstrate how the LabVIEW-based application is developed and how it works. And in the end, I will give some conclusions and I will discuss some ideas for future work. Introduction to power quality and to the developed application. Future's power grids consist of an increasing number of small-scale and dispersed energy generation and consumption devices which generate large amount of data. That increases the electricity sector's need of big data tools and architectures that should enable integration of relevant digital technologies in order to optimize the management and the maintenance of the energy system. One of the greatest challenges in this system is to continuously ensure power supply with high level of power quality. What is power quality? There are different definitions for power quality. Here is given one of them. A good power quality can be defined as a steady supply voltage that stays in prescribed range, steady AC frequency close to a rated value, and smooth voltage curve waveform. Power quality refers to a wide range of variations in the electric power. It can cover wiring issues, grounding problems, load variations, switching transients, and harmonic generations. Its effects often pass through conventional protection networks undetected and can lead to equipment degradation over time. Here are given some examples of power quality disturbances. In this figure, a pure power quality signal is shown. That is a signal that is not disturbed. It has a smooth waveform and a fundamental frequency of 50 Hz. The length of the signal is 0.2 seconds. And this is also known as an ideal voltage waveform. But this waveform is often disturbed by some power quality disturbances. For example, voltage stack that is given with the red line, swell, harmonics, outage, or also known as interruption, flickers, transients, and many other power quality disturbances and also their combinations. In Europe, the quality of the electricity that is provided by a grid operator is defined with the reference parameter set given in the European Standard on Power Quality, EN 50160. When the supply voltage is disturbed, a device draws non-sinusoidal currents and can cause many technical problems such as overheating, malfunction, and early aging. Therefore, poor power quality problem is a problem for a large number of business sectors, especially for the industry. Its cost is high and is rising as the number of power quality disturbances is increasing. That is due to the fact that the effects of these disturbances, such as equipment downtime, increased maintenance activities, and shorter lifetimes, result in financial losses. Therefore, fast and accurate detection and recognition of power quality disturbances is of great importance, and in fact, that is the main aim of the developed application that I am going to present. Here is given on the left side the block diagram of the developed application, while on the right side is the application's user interface or the front panel. From the block diagram, we can conclude that this application is consisted from three main stages. The first one is feature extraction or feature vector construction, the second is classification, and the third is saving the disturbed signals or additional analysis. The input of this application can be two different types of power quality signals obtained from two different sources. The first type is power quality signals obtained with offline generation, or power quality signals read from text file, and the second type are power quality signals obtained with LabVIEW based signal generator that is referenced here. The software that is used for the development of this application is MATLAB, where the feature extraction and the machine learning or the classification is implemented, and of course LabVIEW for the whole development of the application. As I said before, there are three main stages in the application, and the first one is feature extraction. The feature extraction is the most important component or the key component for designing an intelligent system for classification, because it provides information that helps to recognize the faults responsible for the present disturbances. Practice has shown that even the best classifier will perform poorly if the features are not properly chosen. The researchers have introduced different signal processing techniques that are used as a tool for feature extraction. Among all of them, the wavelet transform has been the most extensively used in the last years. Discrete wavelet transform is implemented using the filter bank techniques known as multi-resolution analysis, or MRA. Its basic structure is shown in the figure. The filter bank is used to decompose the signal into different number of levels using a low-pass filter, noted as H0, and a high-pass filter, noted as H1. Since the mirror image symmetry about the frequency omega equal to p-half exists between H1 and H0, these filters are known as quadrature mirror filters. And now here is given the frequency spectra of these filters, analysis filters. The basic idea of the MRA is the idea of successive approximation together with the idea of edit details. The low frequency part of the input signal is split again into two parts of high and low frequencies. Depending on the size of the signal and the type of the application, this process can be repeated several times. As a result, a logarithmic decomposition of the frequency spectra is obtained. Here we can see that at the output of the low-pass filter, H0, the approximation coefficients are obtained, while at the output of the H1 or the high-pass filter, the detail coefficients are obtained. The wavelet transform is in fact a measure of similarity between the mother wavelet and the input signal. This proper selection of the mother wavelet function is the key for performing a successful discrete wavelet transform application. In this work, Dobashi-4 is used as one of the most frequently used wavelets in power quality problems. The number of decomposition levels L of the discrete wavelet transform is also of significant importance. Higher number of levels will bring more information in the system, for example, an extended feature vector, and in that way we will increase the classification accuracy. Additionally, choosing higher number of levels will result in increased calculation complexity of the classification algorithm. Investigational results have shown that increasing the number of levels after 6 do not significantly affect the accuracy of the algorithm. Therefore, in this work, the number of decomposition levels is chosen to be 6. The wavelet coefficients obtained by the multi-resolution and wavelet analysis of the disturbance signal contain effective feature information. This with the detail coefficients obtained at each decomposition level and the approximation coefficients from the last level, the wavelet-based features are obtained and the feature vector is constructed. Here in the table are shown the 9 commonly used wavelet-based features and their mathematical definitions. These wavelet-based features are implemented in MATLAB and are used for feature extraction and for construction of the feature vector. Now I will show how the feature extraction method is implemented in MATLAB. This is the part where the wavelet-based features are implemented using the detail coefficients from each decomposition level for the first level and for the other levels, and the approximation coefficients from the last level. Using these wavelet-based features, the feature vector is constructed. This function is called by the function vectors because in fact here we are working with a set of power quality signals. This function vectors separate each signal from the signal set and then calls the function feature vector in order to construct the feature vector for that signal. The main function here is the function feature extraction, where at first because we need a signal set, the signal set is what? The coefficients of the Dolbesch's-4 filter are taken, and then the vector function is called. In this function there are 4 input parameters. The first parameter is the signal set. The second is the number of the decomposition levels, which is 6, as we said before. And the last 2 parameters are the parameters of the or the coefficients of the Dolbesch's-4 filter, the low pass and the high pass. Let's try this code. It takes a while because it makes a wavelet transform of 11,000 signals. Here is the signal set, the original signal set. 11,000 signals, 640 samples for each signal, and this is the generated set of feature vectors for each original signal. 11,000 signals with 14 samples for each signal. And this feature set is used as an input to the classification method. Classification. As a classification method, in the developed application, the random forest algorithm is used. Random forest represents a combination of tree predictors such that each tree depends on the values of a random vector sampled independently and with the same distribution for all trees in the forest. Because here we are talking about a combination of tree predictors or a set of decision trees, because tree predictor and decision tree is the same. Firstly, I will present what a decision tree means, how it works. This is the basic structure of the decision tree. The operation of the decision tree starts from the node called root node. The next step is division of the records according to their features. The assigned node is called intermediate node, or interior node. And similarly, the next step is assignment of a class label to the nodes. The class label assigned node is called leaf node. Once the classifier is designed, testing of a record using the classifier is a simple approach. Because the random forest is a set of tree predictors, there are different number of trees in the forest. For example, 2 decision trees, 3 decision trees, and so on, 100 decision trees, and even more. How the random forest algorithm works. The input of this algorithm is the feature vector that is constructed in the way that was shown before in MATLAB. This input vector is sampled. From this input vector, the defined number of features are selected, and a subset of the feature vector is constructed, and different subset is constructed for each decision tree, and that is the input of the decision tree. Then the decision tree gives a result, and there are many results. For example, there are 100 trees, there are 100 results. So the result of the random forest is obtained as a majority voting for the final class, or the result is obtained so that the most voted class is chosen, the most voted class by the trees. And that is the final result of the random forest algorithm. Compared to the other classifiers, random forest has a simple structure, a good generalization ability, an anti-noise performance, classification with high accuracy, lower time complexity. It can satisfy the demands of situations when a real-time performance is highly needed. Also, it can meet application needs of massive power quality data for signal classification. One of the main properties of the random forest approach is that it does not overfit as the number of the trees in the forest increases. And because of these properties, the random forest classification method is chosen to be used in the developed application. Here are given the steps of the classification process of the random forest classifier used for the aim of the classification. The first step is the bootstrap resampling technique to extract the training set for every tree in the random forest. Then build 100 decision trees. 6 features are randomly selected from the original feature space to construct candidate segmentation feature subset for each non-leaf node. The feature with the best segmentation performance is finally chosen to split the node. Thus all of the non-leaf nodes are split. If no, then return back, and if the answer is yes, then a simple majority voting method is used to output the optimal classification results according to the classification results for each tree. And now I will show how the classification method is implemented in MATLAB. Here is given the code of the random forest classifier. It is just a one-line code, only the use of the tree-bagger function, and this is a function for training the random forest classifier. This function has only 4 input parameters, but there are other input parameters also, but these are the most important. The first input parameter is the number of decision trees in the forest, which here is chosen to be 100. The second input parameter is the set of feature vectors. The third is a set of classes that correspond to each feature vector or to each signal in the original signal set. Let's see the set of classes. This is the set, The first 1000 classes are the class normal, or signal without a disturbance. The second is swell, sag is the next, harmonic, voltage, sag with harmonic, swell with harmonic, flicker, transient, notch, and spike. In this set there are 11,000 classes, because the feature set is consisted from 11,000 feature vectors. So there are 11 different classes, 1,000 samples for each class. So let's try how this function works. Now this function trains the random forest algorithm, and here is the model of the trained algorithm, the trained classifier. This is the model of the random forest, and here are all of the parameters of the model. Number of decision trees is 100, and if I go here in trees, then here is each tree in the random forest, each separate tree predictor. And I can open these trees also to see the parameters. And also each tree can be separately used as a separate decision tree classifier. But here they are all together used in the random forest model. So this model is safe and is called in the LabVIEW application for classification of the power quality signals. As I said at the beginning, some experimental classification results will be presented because they are important for the accuracy of the classification method. For the aim of the experimental classification, training and testing sets of power quality signals were generated. The generation was made according to the mathematical definitions that are given in this table for the disturbances that are given, and that are normal or signal without a disturbance, sag, swell, voltage or interruption, flicker, oscillatory transient, harmonics, notch, and spike. 11 different classes were considered, as it was shown in MATLAB. 10 cycles were included in every signal. The sampling frequency was 3.2 kHz. On the left side are given the classes that were considered: normal, swell, sag, harmonic, voltage, sag plus harmonic, swell plus harmonic, flicker, oscillatory transient, notch, and spike. The training and testing sets were consisted from 11,000 power quality signals. And now here given the obtained classification results. As we can see from the presented results, there are results for pure signals, signals that are not accompanied with noise, and signals accompanied with 20, 30, 40, and 50 decibels of white Gaussian noise. Why the Gaussian noise is considered? Because in real power systems and in real measurements there is always a presence of noise. So there is a need of a classification method that gives nearly highest accuracy for each noise level. Also, from the presented results, we can see that different number of wavelet-based features are considered for constructing the feature vector, different combinations of the wavelet-based features. Combination obtained as using one wavelet-based features. Combination obtained using two wavelet-based features, three wavelet-based features, 4, and so on to 9 wavelet-based features. From the presented results, according to the need of a classification method that gives nearly highest accuracy for every noise level, and according to these summarized results, it can be shown that the feature combination that is obtained with two wavelet-based features is the best combination, because this combination gives high classification and also is obtained using a smaller number of features. This combination is a combination of Shannon entropy and logarithmic energy entropy. What that means in MATLAB? Here is again the code for where the wavelet-based features are implemented, and here is the construction of the feature vector. And we can see that only two wavelet-based features are used. The Shannon entropy, here is only entropy, but that is the Shannon entropy, and the logarithmic energy entropy. So, according to the obtained results from the experimental classification, the feature vector is shown that the feature vector that is constructed only with two wavelet-based features is an optimal feature vector, because will decrease the computational need for the operations that are needed for the feature extraction method, and gives high classification accuracy. Here I can make different combinations of these wavelet-based features, but for the aim of the developed application, this is the way how the feature vector is constructed and how it's implemented in LabVIEW. And here again are shown the definitions of the wavelet-based features and the selected features that will be used. Demonstration of the developed LabVIEW-based application. Here is given the block diagram of the developed LabVIEW-based application. As I said at the beginning, this application is consisted from three main stages: the feature extraction, classification, and saving the disturbed signals. The feature extraction and the classification were implemented in MATLAB as it was previously presented, and the implementation in MATLAB is integrated in this block diagram. The integration is made using a MATLAB script that is based on a MATLAB code, and in the background it opens a MATLAB command window. So there is a need of a MATLAB installation on the computer where this program runs. If there is no MATLAB installation, then there will be an error and the program will not run. What we have in the MATLAB script? The first line is the path to the folder where the trained model is contained and where the function for feature extraction is contained. According to the model and to the feature vector that is extracted from the original signal, a prediction is made, and the prediction or the output class is the output of the MATLAB script. The input of the MATLAB script is the original signal. As I said before, there are two types of input signals, and this is the front panel of the application, and the type of the input signal is chosen here from a signal generator or reading from a text file. If the toggle button is true, then it reads from a text file, and if it is false, then the program reads from a signal generator. This is the program where when the application reads from the integrated signal generator, and this is the part where the signal generator is integrated. This is how the generator looks like. Here we can define different types of power quality disturbances and different numbers. This generator generates three-phase signal, so we can define disturbances for each phase of the signal. Then the output signal from the generator, the three-phase signal, is separate. Each phase is separate from the three-phase signal, and each phase is passed to the input of the corresponding MATLAB script. There are three MATLAB scripts for each phase, and they are identical. When the output is obtained, the predicted class, it is compared, it is a string, and it is compared with the string normal, which means that there is no power quality disturbance. If the comparison is true, or if they are same, then there is no action, just return back at the beginning with a new signal. But if the comparison is false, if the strings are not equal, then there is a disturbance, and the disturbance is saved. So this is the third stage of the application where the power quality disturbances are saved for future analysis. They are saved in a text file, where this is the path to the folder where they are saved. The name of the text file is the class of the disturbance, as well as the time when the disturbance has occurred and the date when the disturbance has occurred. Besides the saving, this part of the application captures the disturbance and plots on the front panel. This is a plot where the disturbance is shown, and this is a disturbance logger where the disturbances that have occurred are listed. Well, this is the plot where the continuous signal is shown. In case when the toggle button is true, then the application reads from a text file. If this is true, this is the part when the application is reading from a text file. Opening the text file, and here is defined the precision of reading, because here we are working with decimal numbers. With decimal numbers, it is very important how the precision is defined, because it affects the accuracy of the classification. The text file is a set of power quality disturbances. This is the text file. Each column is a different disturbance. It is not that obvious here, but the signals are in columns. And here, with this part of the program, each signal from the signal set is separated and is passed to the input of the MATLAB script. The MATLAB script is the same as in the previous case, where the application reads from a generator. The MATLAB script predicts the output class. The predicted class is compared with the class normal, and the same is happening here. If the comparison is true, then there is no action, just returning back to the next signal. And if the comparison is false, then saving the disturbed signal for additional analysis, capturing on the front panel, and also writing on the disturbance logger for evidence. And this is because 1060 signals are consisted in the text file that are read from the text file. And I think that this is all about the block diagram. So now we can try the application to see how it works. Let the toggle button be true. Let the application read from a text file. If I run the application, I have to choose the text file from which the application will read. And this is the text file, disturbances. And now we'll start reading. Here is the first disturbance, sag. Harmonic plus sag. Here is the continuous signal from the text file. It is one phase signal. Here the last disturbance is shown, is captured, and as I said, this is a disturbance logger where all the disturbances that have occurred are listed for evidence. The date and the time when the disturbance has occurred. Here also the date, the time, the phase, and the class. And let's check the folder where the disturbances are saved. Yes, there are 3 disturbances, and here 3 disturbances are saved for future analysis. If we open, this is the signal. This is the original signal. The application saves the original signal in which a disturbance has occurred for additional analysis. So here are 640 samples from the signal. And here is the date, the time when the disturbance has occurred, the class, the phase, everything that we said before. In the meanwhile, here other disturbances have occurred. Now we can stop the program, the application, and let's try the other case when the application reads from the signal generator. When the signals are obtained using the signal generator that is integrated in the application. In order to use this generator, firstly we have to define disturbances. For example, I will define the following disturbances that would be generated. This is a 3-phase generator, but I will define only in one phase. The first phase, let the first disturbance start at 3.23. The goal value is the amplitude in this case. Let's be a sag, so the amplitude should be lower than this number, because here this is the normal, the amplitude of a pure signal. the signal that is not disturbed. The time when the disturbance ends will be 3.3. It is important that the disturbance should not last longer than 200 milliseconds. There are definitions in the European standard that I have mentioned before for each disturbance, but here for the sac and for the swell, and it is important to not last more than 200 milliseconds. So this disturbance will end at 3.3. The goal value is 0.70711, the value of a pure signal, and that is a sac. Let's define, for example, an interruption. Let the interruption begin at 6.12. The goal value 0.05. The end 6.18. The goal value is the value of the pure signal 0.70711. The next disturbance could be swell, for example. Let the swell start at 12.2 with goal value 1.5. The end of the swell (12.25), 0.70711. And one more disturbance, for example, flicker. Let the flicker start at 16.22. Now here I have to choose flicker amplitude in percent. Let's be 60% of 2. And the flicker frequency in hertz, it can be 60 again, and the time when the flicker ends 16.33, amplitude 0%, and the frequency 0. And let's try. I have to open. Here is the application, reading from the signal generator, so we can start. Here is the three-phase signal, the continuous three-phase signal. I think we generated SAC interruption, swell, and flicker. Yes, here is the stack, the voltage stack. It is listed in the disturbance logger and it is captured here. The time, the date, the phase, the class. The second is interruption, also captured and written in the disturbance logger. There are two more disturbances, swell and flicker. Here is the swell. And one more, and the flicker. And there are no more disturbances because we define only 4. So according to this that was presented, we can conclude that this application provides continuous monitoring of the waveform quality of an input voltage signal, such that it shows the time when a power quality event has happened in the signal, as well as its waveform graph and its class. Moreover, it continuously records the occurred power quality disturbances for future further analysis. Let's see if these signals are saved. Yes, here are the last signals. 1420, 1420. Here are all of the disturbances that were classified in the signal. And we can conclude that the classification was, in the second case, was 100% accurate. So now we can return back to the presentation. Conclusion and an idea for future work. And here we came to the conclusion of this presentation. At this part of the presentation, I want to point out some of the most important things that were said and were shown through this presentation. The first part was presenting the feature extraction method, where the wavelet transform was used as a tool, digital signal processing tool, for feature extraction. It was shown how this transform is implemented in MATLAB, namely the wavelet-based features. And it was also shown how an optimal feature combination is obtained. The length of the feature vector that is constructed directly affects the computational cost of the classification method and of the feature extraction method. So there is a need of an optimal feature combination, because the optimal feature combination is a combination that is consisted from small number of features and has high classification accuracy. For example, in this case of the presented feature extraction method, the optimal feature combination was consisted from two wavelet-based features, the Shannon entropy and logarithmic energy entropy. And this combination was used for feature extraction in the developed application instead of all 9 wavelet-based features, which decrease the computational complexity of the classification algorithm. In the second part, the used classification algorithm was presented, the random forest classifier, and it was shown how this classifier is implemented in MATLAB. It was highlighted what are the most important parameters of the random forest classifier, and that the properties of this classifier and the advantages among the other classifiers that are used for classification of power quality, and that is the reason why this classifier is used. It was shown how the model of the random forest classifier is trained in MATLAB using the tree-bagger function, and how this model is integrated in the LabVIEW based application. The third part was the integration of the MATLAB code in LabVIEW using the MATLAB script node. It was pointed that if this node is used, MATLAB script node, there is a need of a MATLAB installation on the computer where the program will run, because is planned to run, because if there is no MATLAB installation, there will be an error, and the program will not be able to run, because in the background the MATLAB script node opens a MATLAB command window. In the end, the developed application was presented. The block diagram was discussed step by step, and also the front panel of the application. The two different sources of power quality signals were used, and some classification results were obtained. So I think that this presentation will help for developing not only application for classification of power quality disturbances, but also for developing of an application for classification of different type of signals, or for integration of digital signal processing techniques that already exist in MATLAB using the MATLAB script node. And as a future discussion, or an idea for upgrading this application in the future, is making this application to be able to work in real time for classification of real signals that will be measured somewhere in the power system. For that aim, MyRio 1900 will be used. And now only a few words for MyRio. MyRio 1900 is a National Instruments portable input-output device that can be used for design of control, robotics, and mechatronic systems. This device has a processor and FPGA. The processor will be used for the processing part of the application, the feature extraction method, and for implementing the classification method, while the FPGA will be used for measuring, because it has analog inputs. It will be used for measuring the voltage signal that will be classified somewhere in the power system. And in the end, one more time, I want to highlight that this video material is part from the project titled as Innovative Teaching Approaches in Development of Software-Designed Instrumentation and its Application in Real-Time Systems. This project is co-founded by the Erasmus Plus program of the European Union. On this slide, all of the partners that participate in this project are shown. This video material is an output of the Erasmus Plus T-Action 203 with title Strategic Partnership for Higher Education. Thank you for your attention.